Hello. My topic of the project is denoising and reconstruction methods for low-field MRI. The goal is to improve the performance of low-field MRI through denoising and reconstruction approach for noisy and/or unsampled data. So let's review some background. The denoising and reconstruction problem are both inverse problem for MRI, and we can model it in a following way. And usually we solve the problem with regularization that may be modeled according to some prior information. And now I want to introduce some existing methods for denoising and reconstruction. The first is based on the compressive sensing theory, which use the sparsity property of the transformation domain. For example, the wavelet transformation, and it is always used with total variation together. And the second method is BM3D MRI. Block matching 3D transformation denoising is a state-of-the-art denoising method, and here we only want to use the first step of the BM3D denoising, which is that we group the image matches and use some 3D transformation and hard thresholding, inverse thresholding to get an estimated version of the noisy data. And it's similar to the sparsity as the compressive sensing. And in BM3D MRI, the author decoupled the problem into two steps. The first is a deblurring problem, and the second is a denoising problem, which realized by a 3D analysis sparse transformation, and by update the estimated result iteratively, we can get a BM3D sparse result, and which tend to be good denoising result. And next I want to introduce a low rank matrix property based method, LOREX. Now let's say we have an image rho xy, and it has limited image support omega rho, and we can always find at least one function fxy which is always 0 within the support of the image rho xy. So we can always say that rho xy times fxy equal to 0 everywhere, and use convolution theorem. We got an equation in frequency domain that we can construct a low rank matrix C here. Since we can find many f for C, such that C times f approximately equals to 0. So the C matrix is hopefully a low rank matrix. And now I want to say something about auto-calibration case. With auto-calibrated sampling, we can always find some fully sampled columns in C matrices, and that we can estimate the null space of the C matrix through SVD. And we can say that the C times V conjugate approximately equal to 0. That's we can use it as a regularization term here, and we can use the following two models for the ACLORAX. The first is similar to the commonly used method that approximates the whole K-space or whole image together, and the second model is that we only want to estimate the unsampled position of the data and use the sampled data directly. And the second model may not be able to do some denoising work. So yeah. And with these three methods, and inspired from the decouple methods from the BM3D MRI, I want to say that whether we can decouple the problem to two stages for the undersampled noisy data. The first step is a reconstruction problem, and the second is a denoising. And I want to say whether we can combine a reconstruction levelization with a denoising one. And though it is not reasonable to classify these prior information, but I just want to try to combine them together, so I made a classification here. And with this thought, I will attempt to reconstruct the data in two ways. The first is to combine the acylorex with wavelet sparsity. In this way, I add a L1 regularization term of the wavelet transformation to the acylorex model, and it can be solved by an ADM approach. And the second is with the help of the decoupling, I can combine the BM3D with acylorex reconstruction. And now let's say some results. Before that, I want to say something about the simulation settings. The data source is from the Lorex software, and since I have no access to low-field data now, so I simulated it by adding white noise and K-space. And the methods I will compare are wavelet sparsity and acylorex and their combination. And I also I tried some BM3D, and but I have not got a good result. So I will say something about that, but I will not compare them. And here are the ground truth single image and the noise data, and the sampling mask I will use, and the last one is the zero fitting result from the undersampled data. And the first case is a fully sampled denoising. We can say that the wavelet sparsity result is smooth, but the MSE performance is not good, and the original acylorex has a good MSE, but we can see some noise visually. So by introducing a wavelet sparsity, we can say that the result remove some noise within the support here and got a relatively better MSE. And the second case is the noises reconstruction. Now we can see that acylorex performed well in this case, since it's really a good reconstruction method here, and the performance of wavelet sparsity is not good. And introducing the wavelet sparsity will not help the performance much. So finally, we have undersampled denoising problem. So, and we can see that the wavelet sparsity reconstruction is not good, and we can see that by introducing the sparsity to acylorex, we can improve the performance to some degree. And here is one iteration BM3D threshold result. We can see that some blocks have some unrealistic good denoising effect, but maybe I can improve the block matching method and try to plug it into a decoupled solver in the future. And the other things that we can do is to optimize the parameters and reduce the computation complexity, and of course do more experiments on different real data sets. And that's it.